Hello everyone, myself Shreya Dhote. My roll number is BT21CME111. Today I will be discussing the Evaporative Light Scattering Detector, which is also called ELSD, a type of detector widely used in a liquid chromatography applications, particularly for non-volatile and semi-volatile compounds. Let's start from the by knowing definition. The evaporative light scattering detector, commonly referred to as a ELSD, is a type of detector used in liquid chromatography. It's particularly effective for detecting compounds that do not absorb UV light, which are otherwise challenging to analyze with traditional detectors. Why use ELSD? Challenges with UV detectors. Many compounds like carbohydrates, lipids, and polymer lack chromophores, meaning they don't absorb UV light. This makes them invisible to UV detectors, limiting their analysis. ELSD has a solution. ELSD detects analytics based on their ability to scatter light rather than absorb it, which allows for detection of broad range of non-volatile and semi-volatile compounds. Key characteristics of ELSD. Universal detector. ELSD is considered a universal detector for non-volatile compounds because it can detect almost any substance that forms solid particles after the evaporation of its solvent. Independence from optical properties. Unlike UV or fluorescence detectors, ELSD doesn't require analytes to have specific optical properties like absorbance. This makes it extremely versatile. Where is ELSD commonly? Industries and fields. ELSD is popular in pharmaceuticals, food and beverage analysis, a material science. It is widely used for quality control, research and regulatory testing of complex samples that contain non-UV active compounds. Let's see the basic working principles of ELSD. Let's start with first part, which is nebulization. The sample solution containing both analytics and solvents enters a nebulizer process. The nebulizer converts the liquid sample into fine mist or aerosol consisting of tiny droplets. It's important is that this step creates a dispersed form of sample, preparing it for the next stages of evaporation and detection. Second part is evaporation. The aerosol mist is passed through a heated tube where the solvent evaporates. It results in non-volatile analytes are left behind and as fine solid or semi-solid particles, while a volatile solvents are removed. Its important point is that only compounds that do not vaporize at the evaporation temperature are retained for detection. Volatile compounds are lost, which is a limitation of ELSD. Third part is light scattering and detection. The particles enter in detection chamber where they are exposed to laser beam. Scattering effect. When the laser hits the particles, they scatter the light in all directions. Detection. A photodetector captures the scattered light, creating a signal. The intensity of the signal is proportional to the amount of analyte present. Uniqueness of ELSD. Unlike UV detectors, the signal does not depend on optical properties of analytes, but rather on its physical presence and quantity. Here we can see that experimental setup, which is divided into three parts: nebulization, evaporation, and light scattering and detection. Let's see forward components of evaporative light scattering detector. Let's start from the nebulizer part. Its function is to convert the liquid sample into a fine mist, aerosol of small droplets. Its working is like that: the sample solution containing both the analytes and solvent enters the nebulizer. It is broken up into fine droplets using either a gas flow or other mechanical forces. Its importance is that this stage is essential for producing uniform droplets, which ensures consistent evaporation and reliable detection. Its second part, evaporative tube. Its function is like that, heats the aerosol to evaporate the solvent, leaving behind only non-volatile analytes as a solid particles. In this process, the aerosol mist moves through a heated tube chamber where the solvent evaporates. Its important point is that temperature control is critical in this step. The heat must be sufficient to evaporate the solvent without decomposing or losing non-volatile analytes. Its limitation is that highly volatile analytes may evaporate along with solvent, which can reduce detection accuracy for such compound. Let's see the third part, detection chamber with light source and photodetector. Light source. The particles that remains after evaporation are exposed to focused laser beam in the detection chamber. Scattering and detection. As the laser light hits the particles, it's scattered in various directions. The photodetector then captures the scattered light, producing a signal. That signal generation, the strength of the scattered light signal is proportional to the mass of analyte particles. Its unique aspect is that this component allows for detecting analytes based on the physical particle presence, independent of their optical properties like UV absorption. ELSD's design allows it to detect a wide range of compounds without the need of chromophores or other optical characteristics. This makes it universal detector for non-volatile compounds in liquid chromatography. Let's move forward and see the types of analytes detector with ELSD. Let's see first about carbohydrates. Its examples are glucose, fructose, lactose, and other sugars. Its application is that it is widely used in food and beverage analysis to quantify the sugar content in the products. Why only ELSD? Carbohydrates generally lack chromophores, so they don't show up well with UV detectors, making ELSD as an ideal choice. Second is lipids and fats. Its examples are triglycerides, fatty acids, and oils. Its application is that it is used in nutritional analysis, especially in food and cosmetic industries, where lipid content is a key quality and regulatory measure. Why only LSD here? LSD can detect lipids due to their semi-volatile nature, making it suitable for analyzing non-polar compounds that are invisible to UV detectors. Third is polymer and large molecules. Its examples are synthetic polymers, polysaccharides, and other large macromolecules. Its application is that quality control in material science and pharmaceutical research for analyzing polymer properties and purity. Since these molecules do not contain UV absorbing groups, ELSD is a practical solution for polymer analysis. Fourth part is pharmaceutical compounds. Its examples are non-active ingredients in drugs such as binders, fillers, and coatings. Its application is that pharmaceutical quality control to ensure accurate compositions of drugs. Many excipients lack UV active groups but are critical for product quantity and safety. Let's see the advantages of ELSD. Let's start with the advantages of ELSD. First is the universal detection for non-UV active compounds, which is it detects a broad range of non-volatile and semi-volatile compounds, including those without UV absorption such as sugar, lipids, and polymers. And second is sensitivity and reproductivity. It provides reliable, consistent signals for a variety of sample types, making it useful in applications requiring precise measurements. Third is non-dependency of optical properties. Unlike UV or fluorescence detectors, ELSD doesn't require analytes to have specific optical characteristics, allowing it to detect compounds regarding of their absorption spectra. Fourth is versatile application across industries. Widely used in food, pharmaceuticals and material science for quality control due to its ability to detect diverse compounds. Let's see the limitations of ELSD. First is that it is not suitable for highly volatile compounds. ELSD can only detect non-volatile or semi-volatile compounds. Highly volatile compounds evaporated during the evaporation stage, making it undetectable. Its implication is that this limits the use of ELSD for compounds with low boiling point. The second is lower quantitative accuracy compared to mass spectrometry. While ELSD provides concentration-related signals, it is not precise or quantitative as mass spectrography, which can provide detailed mass information and greater sensitivity. And its implication is that ELSD may not be best choice when highly accurate quantification is needed. Its third part is the dependency on proper solvent selection. Certain solvents can interfere with detection if they do not evaporate completely, or they can cause issue with particle formation. Its implication is that careful selection and optimization of solvent are required to avoid signal interference. Fourth is the cost and maintenance requirement. ELSD systems tend to be more expensive and require more frequent maintenance compared to simple detectors like UV detector. Implication: this may increase the operational cost, particularly for smaller labs of application with budget constraints. Let's see the comparison with other detectors. First one is ELSD and U versus UV detectors. Its detail basis. ELSD detects non-volatile compound based on light scattering independent of the compound optical properties. UV detector relies on UV light absorption, so it only detects compounds with chromophores, UV actives. Its limitation is that UV detector cannot detect non-UV active compounds like sugar, lipids. ELSD therefore is ideal for compounds that do not absorb light, making it more versatile in certain applications. Second is ELSD versus mass spectrometry. Its detection principle is that ELSD provides concentration dependent signal based on scattered light, which work well for semi-quantitative analysis. Mass spectrography provides both qualitative and quantitative data with high sensitivity and specificity. Its complexity and cost. Mass spectrometer is complex, expensive, technique require specialized skills, while ELSD is generally simple to operate and maintain, making it suitable for routine application. Use case consideration. ELSD is effective for screening large quantities of non-volatile, and while mass spectrography is preferred for application of needing detailed molecular analysis. Let's see the application of ELSD in various fields. First one in pharmaceuticals. Drug formulation. ELSD is used to analyze both active pharmaceutical ingredients and excipients, active ingredients that lacks chromophores. Quality control. Essential for detecting compounds like binders, fillers, and coating agents in drugs to ensure consistency and safety. Its example is that analysis of lactose and other excipients that don't absorb UV light but are critical to drug composition. Second is food and beverage industries. In the nutrition analysis, quantifies sugar, fats, and other components in food and beverage that lack UV absorption. Quality and safety testing, used for verification of carbohydrates and lipids content, which are important for labeling and regulatory compliance. Its example is that determining fat content in a dairy product or a sugar level in a beverages, their traditional UV detectors are inserted. Let's see the recent advancement in ELSD technology. First one, it is that it improved sensitivity and detection limits. Enhanced detection, newer ELSD models have improved sensitivity allowing for detection of lower concentration analytes is beneficial for the enhancement of broadens ELSD applicability in trace analysis, making it more competitive with other sensitive detection methods. Second is automated and user-friendly design. Automation, modern ELSD system, other feature automated calibration and cleaning, reducing the need for manual intervention. User interface improvement. Advanced software interfaces allow for easier control and monitoring, improving usability and efficiency in routine applications. It is beneficial. This advancement makes ELSD more accessible for routine lab use, reducing downtime and maintenance. Third part is compatibility with hybrid detection systems, multi-detector setups. ELSD is increasing used to alongside detectors like mass spectrometry and UV in hybrid configurations. It's beneficial. Hybrid setups combines ELSD broad detection capability with precise of mass spectrography or the simplicity of UV, enabling comprehensive samples analysis in a single run. Fourth is eco-friendly design. Reduce solvent consumption. Some ELSD systems are now designed to work with smaller volumes of solvent, minimizing the waste. Lower power consumption. Energy efficient design makes ELSD more sustainable and cost effective. It is beneficial that it implements the support greener lab practices and lower operational cost. Let's see the future trends in ELSD technology. First one is integration with multi-detector system combining ELSD with techniques like mass spectrography for more accurate and comprehensive data analysis. Second is miniaturization and portability. Development of compact portable ELSD units for on-site and field-based testing. Third is AI and automation. Using AI machine learning for enhanced data analysis, automated maintenance and improved system efficiency. Thank you.